All right, you've probably heard this term RAG getting thrown around a lot lately. It stands for Retrieval Augmented Generation, and honestly, it's the key to solving one of the biggest headaches in AI today. So we're going to decode exactly how RAG is teaching AI to give answers based on, actual facts, not just making stuff up. Let's dive in.
So, let's start with a problem I'm sure we've all run into. You ask a chatbot a pretty specific question, right? Maybe about a company policy or something, and you get back this answer that sounds super confident, but it's just completely wrong. We call that a hallucination, and it happens for a really simple reason. The AI just doesn't have the right context. It's flying blind.
And this right here, this is a perfect example. The AI says, hey, I don't have your private documents, but typically the policy is, it's giving you a generic internet-based answer because it's missing that crucial private context. It knows a little bit about everything, but it doesn't know your specific stuff, so it guesses. And, well, guessing just isn't good enough, is it?
Okay, so here's our mission. We're going to transform that generic, kind of clueless LLM into this super smart policy co-pilot. We want to go from an AI that only knows what's on the public internet to one that knows our private company documents inside and out. We're talking about moving from made-up answers to factual, verifiable answers that can even cite the exact source. So, how do we actually build this thing?
Right, so how do we fix this whole knowledge gap? Well, the very first step is to give our chatbot a memory, a real working memory that lets it connect to and actually understand our specific private documents.
And that, my friends, is exactly what RAG is. It's basically a technique that acts as a bridge. Think of it like this. It connects the powerful, massive brain of a large language model to a specific external knowledge source, like, say, your company's policy documents. And the process itself? It's kind of brilliant in its simplicity. It really just breaks down into 3 steps. First, you retrieve the most relevant info from your documents. Then you augment the user's question by just tacking on that info as extra context. And finally, you ask the AI to generate an answer using only the stuff you just gave it. It's like giving the AI an open book exam. It doesn't have to guess anymore. It just has to read.
Okay, that makes sense. We retrieve the right information, but what if the user doesn't use the exact perfect keywords that are in the document? This is a huge problem, and it leads us to a much smarter way of searching.
And that's the huge difference between old-school keyword search and what we call semantic search. Keyword search is super literal. You search for home office, and if the document only says work from home, you get nothing. Zilch. Semantic search, on the other hand, is way smarter. It gets the meaning behind your words. It knows that home office, work from home, and remote work are all basically talking about the same thing.
So how on earth does a computer understand meaning? Well, the magic here is a concept called embeddings. Basically, a special AI model, an embedding model, takes a piece of text and turns it into a big list of numbers. We call that a vector. You can think of this vector as coordinates, like on a map, but instead of a map of places, it's a giant map of ideas and concepts.
And this meaning map idea is so cool. See, just like on a real map where cities are close together, concepts with similar meanings, like reimbursement and allowance, get placed really close to each other in this space. So the AI can just measure the distance between the coordinates of your question and the coordinates of all the document pieces. The closest ones are the most relevant, even if the words don't match at all.
Now you might be thinking, don't you need a gigantic, supercomputer-sized AI to create these embeddings? And the answer is surprisingly no. This is one of the cleverest parts of the whole system. We actually use 2 different kinds of models. For the embedding part, just finding the meaning, we use these small, super efficient models. They're fast, they're cheap. We only bring out the big guns, the giant generative models like GPT, for the very last step, which is what they do best, writing a beautiful, human-like answer based on the facts we found.
Okay, so we figured out how to search by meaning. That's huge. But now, how do we organize all of our documents so that this search is lightning fast and efficient? We basically need to build a smart digital library for our AI.
And let's be practical for a second. If a user asks a simple question about remote work, are we really going to give the AI the entire 50-page employee handbook and just say, good luck, figure it out? No way. That's totally inefficient, and it would just overwhelm the AI. We need to be way more precise than that.
The solution is a process called chunking, And yep, it's pretty much exactly what it sounds like. We take our big, long documents and we just break them down into smaller, more manageable pieces or chunks. It's like taking that giant handbook and digitally ripping it into individual focused paragraphs.
But here's the thing. Chunking is a real balancing act. If you make your chunks too small, you can lose super important context. Imagine a chunk that just says, dogs are allowed, but the rest of the sentence, only on Fridays, is in the next chunk. That's a problem. But if your chunks are too big, well, you're right back where you started, giving the AI way too much irrelevant information.
So, once we have all these perfectly sized, meaning-infused chunks, where do we put them all? We store them in something called a vector database. I love this analogy. Think of it as a hyper-efficient genius librarian for our AI's memory. It's built specifically to store millions of these number vectors and uses these really clever indexing tricks to find the best matches to your question almost instantly.
All right, we have all the pieces of the puzzle now, right? We've got semantic search, we've got embeddings, chunking, and these cool vector databases. So now let's put it all together and see how the whole RAG pipeline actually works.
And here it is, the whole shebang from start to finish. So first, there's this one-time setup, the ingestion phase. We chunk our documents, turn every single chunk into an embedding, and load it all into our vector database. Then, whenever a user asks a question, we take that question, embed it, and use it to find the most similar chunks in our database. We then combine the user's question with those chunks, and that's what we send to the big LLM to generate a final, fact-based, totally accurate answer. See how it all connects?
So we have the blueprint, the master plan. But making this actually work in the real world, making it fast and reliable for potentially thousands of users, that's a whole different ballgame. Let's talk about what it really takes to put RAG into production.
The number one enemy in the real world is latency, or, lag. Every single step in that pipeline, the embedding, the search, the final generation, it all takes time. If you don't optimize it, a single question can take almost a full second to answer. And for a real-time chatbot, that's an eternity. People will just click away.
So how do we solve this major speed problem? The answer is actually pretty simple, and it's a classic in computer science: caching. By smartly storing the results of stuff we've already done, we don't have to do all that heavy lifting every single time. And the results, they are absolutely dramatic. Look at this. Caching can make the system up to 190 times faster. We're talking about going from a sluggish 950 milliseconds down to just 5 milliseconds. That's a total game changer. And this isn't just one simple trick. Caching is a whole multi-layered strategy. You can cache the embeddings for common questions, you can cache the search results from the vector database, and, this is the big one, you can cache the final answer from the LLM itself, because that generation step is usually the slowest part. Caching at every stage just makes the entire system feel incredibly snappy and responsive. So if there's just one thing you take away from all this, let it be this simple idea. RAG gives an AI an external memory. It's the technology that transforms a brilliant but, kind of forgetful genius into a true knowledgeable expert on any specific topic you want.
And that leaves us with a pretty mind-blowing question for the future, doesn't it? Now that we have a reliable way to securely teach an AI any private knowledge base, I'm talking medical research, legal documents, your company's entire internal wiki, what incredible new problems are we all going to solve next? The possibilities are just massive.